In our little corner of the galaxy, we've found thousands of exoplanets. Hundreds of them seemed perfect, so-called super-Earths in the habitable zone, bigger than our own world, and sitting at just the right distance from their star for liquid water. The media, and even scientists, were buzzing. Were these prime candidates for alien life? Or was this galactic real estate boom just a mirage? What if the most promising planets on our list are actually scorching, toxic hells? One planet forced us to confront this exact possibility. It was a wake-up call that fundamentally changed how we search for life, and its name is Kepler 69c. When NASA's Kepler Space Telescope launched back in 2009, it had one profound job: to figure out if Earth-like planets are cosmic rarities or a dime a dozen. For nearly a decade, it just stared at one patch of sky, watching over 150,000 stars for tiny periodic dips in their brightness. This was the transit method, catching the shadow of a planet as it passed in front of its star. The technique was a game changer, revealing that there are more planets in our galaxy than stars. Among the most thrilling finds was a whole new class of planet we don't have in our solar system: the Super-Earth. These are worlds bigger and more massive than Earth, but smaller than giants like Neptune. Immediately, they shot to the top of the most wanted list for habitable worlds. The thinking was that a bigger planet could mean stronger gravity, which is great for holding on to a thick, life-sustaining atmosphere. More mass could also power more geological activity, a planetary engine that helps regulate climate for billions of years. For a while there, astronomers were electric with optimism. We were finding these apparently perfect worlds in the habitable zone of their stars, that sweet spot where temperatures could allow for liquid water. But science is all about questioning your assumptions, and the story of Kepler 69c is a masterclass in why. Initially celebrated as a huge step toward finding another Earth, a closer look at this single world forced us to rethink everything. It suggested our idea of the habitable zone was dangerously simplistic, and that many of our star candidates might be super Venuses in disguise, worlds doomed from the start to become runaway greenhouse nightmares. This is the cautionary tale of Kepler 69c, and why the galaxy might be filled with far more hellscapes than havens. Before Kepler, our exoplanet catalog was pretty slim. We mostly found hot Jupiters, massive gas giants orbiting way too close to their stars, simply because their enormous size and speed made them the low-hanging fruit for ground-based telescopes. We had no idea if smaller rocky worlds like ours were common or not. Kepler changed everything. The mission was an engineering masterpiece. Its main instrument was basically a super-sensitive digital camera, hooked up to a huge mirror, tasked with measuring starlight with insane precision. The logic was simple. If a planet's orbit is lined up just right, it will cross in front of its star from our point of view, causing a tiny dip in light. How much it dims tells you the planet's size. How often it happens tells you its year. See it happen 3 times, and you can be pretty sure you found a planet. This method opened the floodgates. By 2011, Kepler was finding entire solar systems. But the real prize was finding planets in the circumstellar habitable zone, which the public quickly nicknamed the Goldilocks zone. It's an easy metaphor. A planet too close to its star is too hot, and its water boils off like on Venus. Too far, and it's a frozen wasteland like Mars. But in that temperate zone in between, things are just right for liquid water. The concept itself wasn't new, but it was refined in the 90s by astronomer James Casting, whose models on how atmospheres interact with starlight became the gold standard. And this zone moves. It's further out for hot, bright stars, and much closer in for cool, dim ones. Into this framework came the super-Earths, ranging from about 1.25 to 2 times the size of Earth. They seemed to have it all. In theory, their higher gravity could help them hang on to a protective atmosphere. Their larger iron core could generate a strong magnetic field to shield that atmosphere from the star's solar wind. And more mass means more internal heat, driving plate tectonics, the geological process that regulates Earth's climate and prevents it from getting stuck in a permanent freeze or a runaway heat wave. For a time, it felt like every new discovery was getting us closer to answering the big question: are we alone? The galaxy seemed to be packed with worlds that weren't just Earth-like, but maybe even better than Earth. But in science, optimism always has to answer to data. And one of these poster child planets was about to deliver a serious reality check. In April 2013, NASA announced the discovery of 3 new super-Earths in the habitable zones of 2 star systems, Kepler 62 and Kepler 69. One planet in particular got top billing, Kepler 69c. Located about 2,700 light-years away, it was about 70% larger than Earth. What made it so special was its star. Unlike many other candidates found orbiting cool red dwarfs, Kepler 69c was orbiting a G-type star named Kepler 69, a star very much like our own Sun. At the time, one scientist called it our first habitable zone super-Earth around a Sun-type star. The initial numbers were tantalizing. Its radius was pegged at 1.7 times Earth's, and it zipped around its star in 242 days, an orbital period eerily similar to Venus's 225-day year. Despite that little red flag, the planet was declared to be in the habitable zone, making it a prime candidate to host alien life. The announcement sparked a wave of excitement, complete with artistic renderings of a lush, water-covered world. But this is where the scientific process kicks in. A team led by researcher Stephen Kane decided to take a closer look. They knew that even in the initial announcement, astronomers weren't sure about the planet's actual composition. Was it even rocky? And that Venus-like orbit was suspicious. Kane's team did a fresh analysis, focusing on 2 key things: the star's properties and the real boundaries of the habitable zone. First, the star Kepler 69 is indeed like our Sun, but it's a bit older and has changed over its lifetime. More importantly, Kane's team applied newer, more rigorous climate models to define the habitable zone. The original announcement was based on a slightly more generous definition. The updated calculations, published just a few months later, painted a very different picture. Their work showed that Kepler 69c wasn't comfortably inside the habitable zone at all. It was right on the razor's edge, receiving far more heat than first thought. This new position was alarming. Venus orbits just inside the inner edge of our Sun's habitable zone, and it's a hellscape. Its surface is 462 degrees Celsius, 864 degrees Fahrenheit, and the air pressure is over 90 times that of Earth's. What doomed Venus was getting just a little too much solar radiation, which triggered a runaway greenhouse effect it could never escape. Kane and his colleagues calculated the amount of energy Kepler 69c gets from its star. The number they landed on was the smoking gun. Venus gets about 2,611 watts per square meter from the Sun. Kepler 69c gets 2,614. The similarity was undeniable. The dream of a habitable water world evaporated, replaced by a new terrifying hypothesis. Kepler 69c wasn't a super-Earth. It was our first candidate for a super-Venus. The transformation of Kepler 69c from paradise to inferno in our scientific models all comes down to one catastrophic process: the runaway greenhouse effect. To picture what a super-Venus is, you first have to understand what happens to our own Venus, and then imagine it on steroids. Here on Earth, the greenhouse effect is a good thing. Gases like water vapor and CO2 in our atmosphere let sunlight in, but trap the heat that radiates back out. It keeps our planet from being a frozen ball of ice. But this system has a tipping point. A runaway greenhouse event is a vicious feedback loop. It starts when a planet gets too much energy from its star. This heat evaporates more water from oceans. And since water vapor is a powerful greenhouse gas, the atmosphere traps even more heat. This, in turn, makes the surface hotter, which evaporates even more water. The cycle feeds itself until the oceans literally boil away. The planet becomes shrouded in a thick, steamy blanket. At these temperatures, even rocks on the surface can start to bake and release massive amounts of carbon dioxide, adding even more fuel to the fire. The end result is a sterile world with a crushing, superheated atmosphere. That's what we believe happened to Venus. Now, apply this to a world like Kepler 69c. Its higher gravity would allow it to hold on to a much thicker atmosphere to begin with. If it started with large oceans and sat where the energy models say it does, the runaway process would be amplified. A thicker starting atmosphere and more massive oceans would mean more water vapor to feed the feedback loop. The final atmospheric pressure on a super-Venus could make Venus's 90-bar pressure look tame. We'd be looking at a world with a surface temperature hot enough to melt rock. The fate of a planet, whether it becomes an Earth or a Venus, is a delicate balancing act of three things. Stellar insolation. This is the big one. How much energy it gets from its star. Cross a certain threshold and you trigger the runaway. Planetary albedo. How much light the planet reflects. Clouds play a huge role here. But as we see with Venus, even highly reflective clouds can't save a planet if the greenhouse effect is strong enough. Atmosphere. How much and what kind of greenhouse gases a planet starts with. A denser atmosphere makes a planet more vulnerable. When scientists ran climate models for Kepler 69c, with its known size and orbit, the simulations consistently pointed to one outcome: a world that had long since boiled its oceans away. But there's another twist. Later research has suggested that planets in Kepler 69c's size range, between 1.5 and 2 times Earth's radius, might not even be rocky. Many of them could be mini Neptunes, worlds with a rocky core surrounded by a massive, hydrogen-rich atmosphere. If that's the case, Kepler 69c was never a super-Earth to begin with, but it's still a hellscape, a scorching, uninhabitable gas planet. Either way, the lesson was clear. It was built in the wrong neighborhood. The re-evaluation of Kepler 69c was more than just a fact-check on a single planet. It sent shockwaves through astrobiology. If a world that looked so good on paper could be so catastrophically inhospitable, what about the hundreds of other planets we'd labeled potentially habitable? It forced us to face an unsettling conclusion. Our map of the habitable zone was wrong. This led Kane's team to propose a new, much more dangerous region of space, the Venus zone. This is a hypothetical zone around a star where a rocky planet is all but guaranteed to suffer a runaway greenhouse effect. The scary part is that the inner edge of the classic habitable zone and the outer edge of this new Venus zone are dangerously close and may even overlap. Many of the planets we were cheering for were likely deep inside this Venus zone all along. It turns out the Goldilocks region is a lot smaller and more precarious than we first thought. This has huge implications for the Fermi paradox. You know the one. If the universe is so big and full of planets, where is everybody? To solve the paradox, some scientists propose the idea of a great filter, a challenge so hard to overcome that it stops most life from becoming a spacefaring civilization. People have speculated that the filter could be the jump to multicellular life, or maybe civilizations just inevitably blow themselves up. But the story of Kepler 69c suggests a quieter, more planetary filter. Maybe the great filter isn't nuclear war or an asteroid. Maybe it's just bad real estate. Maybe the laws of physics dictate that the vast majority of rocky planets that seem to be in the right place are destined to be sterilized by their own atmospheres. The reason the cosmos seems so quiet might be that the number of truly, persistently habitable planets is way lower than our early estimates. The set of conditions needed for a stable, life-bearing climate for billions of years, the right size, the right atmosphere, plate tectonics, a magnetic field, and a very specific and narrow orbit is just extraordinarily rare. Our understanding is evolving, moving from a simple checklist to a much more complex, systems-level view of habitability. We now know we can't just look for a planet in the right zip code. We have to look for one that survived. This constant refinement of what makes a planet truly livable is one of the biggest challenges in science today. It's a messy, fascinating process of discovery and correction, and it leads to a critical question as we refine our search. What do you think the greatest barrier to finding ET is? The vast distances, our own tech, or as Kepler 69c suggests, our own assumptions about what habitable really means? Let me know your thoughts in the comments. The story of Kepler 69c marks a pivotal, sobering moment in our search for life. It's a journey from wild optimism to a more careful, scientific precision. We started with the thrilling idea of super-Earths, defined a habitable zone based on liquid water, and found what we thought were dozens of candidates. But Kepler 69c was the cautionary tale. Through painstaking analysis, our understanding of it shifted from a potential water world to a super-Venus candidate, a victim of its own atmosphere. It forced us to accept that the habitable zone isn't a broad, friendly neighborhood. Its inner edge is a cliff, and many of the planets we thought were safe have likely fallen off into a Venus-like inferno. But this isn't a reason to be pessimistic. It's a reason to be precise. And now we have the perfect tool for the job, the James Webb Space Telescope. JWST can do what Kepler never could: analyze the atmospheres of these distant worlds. It can look for chemical fingerprints of life, or biosignatures. But just as importantly, it can look for the anti-biosignatures of a hellscape. By searching for a thick CO2 atmosphere or other telltale signs of a scorched world, JWST can help us finally test these models and separate the super-Venuses from the truly promising worlds. JWST is already looking at planets like 55 Cancri E, another super-Earth, and finding tantalizing evidence of a substantial atmosphere, possibly rich in carbon dioxide or carbon monoxide. The results are still being fiercely debated by scientists, which is exactly how the process is supposed to work. The galaxy may not be as crowded with Earth twins as we once hoped. The great filter of planetary physics may have sterilized countless worlds. But that just makes every new, truly promising candidate that much more precious. The search for life got harder, but our tools and our theories are sharper than ever. Thank you for joining this deep dive into the super-Venus problem. The story of Kepler 69c is a perfect example of how science works, by correcting its own assumptions to get closer to the truth. In our next video, we'll explore the incredible engineering behind the atmospheric sensors on the James Webb Space Telescope. We'll look at how instruments like NIRSpec and MIRI actually capture and decode the light from these distant worlds to give us the data we need to answer the very questions we've raised today. Thanks for your time, and never stop questioning.